Welcome to this video in the Ionic and Metallic Bonding chapter. This is video 6.2, where today we will cover the properties of ionic compounds. We're going to discuss ionic bond strength based on lattice energy, introduce table S, and how you can use the absolute electronegativity difference to evaluate the degree of ionic character or ionic bond strength, and talk about how the structure of an ionic compound will explain all of the observed properties that we are supposed to know. If you have not already done so, please make sure you have your chemistry notebook handy, have a periodic table at the ready, and a writing utensil to take notes. We got a lot to do today, so let's get cooking. Let's start today's video off by talking about the properties of your ionic compounds. It's going to be important to know these because you are going to have to be able to identify an ionic compound just by looking at the observed properties. In honors, you're also going to have to understand how the structure of the ionic compound will actually explain the properties that you guys see. So that really sits back onto our essential question of how does structure dictate properties? Well, we're going to answer that in today's ionic video. So the first thing you guys have to know is that ionic bonds are going to be the strongest of all the three primary bond types. And those three are listed here: ionic bonds, covalent bonds, and something called metallic bonds that you guys haven't learned yet, but we're going to get to at the end of this unit. I do want to call your attention to the three second types of bonds, and I wouldn't even call them bonds. I would call them attractions, because they are going to be your intermolecular forces. They are your hydrogen bonds, your van der Waals forces, and your dipole attractions. We are going to get into those later on as we get further into both the covalent and ionic bonding units. Since ionic bonds are strong, let's start talking about how we would rank or quantify ionic bond strength. And the way we're going to do that is by using two concepts, one called lattice energy and the other one called END, which is an acronym that stands for electronegativity difference. To help you make sense out of both these concepts, you have to understand that the ions in an ionic compound are arranged in a crystal lattice. Now, you see this lattice here below. The crystal lattice is made up of all of these formula units, and those formula units come as juxtaposed positive and negative ions. Here you can see that the positive is always flanked by a negative, and the negative is always flanked by positives. The formula unit itself is the simplest whole number ratio of the ions in the formula of the ionic compound. So the term formula unit is reserved specifically for ionic compounds, whereas in covalent bonding, we would use the term molecule to represent sort of the same thing. Now, why do we care about this? Well, the strength of the attraction between the ions in an ionic bond is better known as lattice energy. The relationship is simple. When an ionic bond forms, the greater the lattice energy that's released, the stronger the bond is going to be. And it's a pretty complicated calculation that you guys can see down here. Let me just break down what some of the variables are, because you're really not going to have to calculate lattice energy in chemistry honors, and you're probably not going to have to calculate it in AP either, but you do need to understand the qualitative relationship. So the relationship of the variables is simple. The Q's that we see here are important. They represent the charge of the first ion and the second ion that is in your ionic compound. So for instance, if we were dealing with NaF, sodium fluoride, the charge of the first ion, Q1, would be a +1. The charge of the second ion would be a -1. And you notice here we have to take their product and multiply them together. +1 times -1 gives us a -1. We're going to take the absolute value for Q. So that would wind up being a +1 in a case like that. The other variable that's really important is this bottom one here in the denominator of the formula, and that is the distance between the ions in the ionic bond. I'm going to make it even simpler than that. It's the size of the ions. These two things are the two determining factors in how strong the bond is and how much lattice energy actually gets released. So let's simplify it here. Basically, you want to know how strong your ionic bond is? Well, in the bonded pairs of ions, ions that have larger charges are going to bond more strongly than ions that have smaller charges. So +2 ions or -2 ions are going to bond more strongly than +1 or -1 ions. Also, ions that are smaller are going to be more strongly attracted than ions that are larger. And this we remember back in the periodic table chapter, where we start to talk about how size influences attraction. If we wanted to do an example and say, well, all right, guys, which of these ionic compounds has the stronger bond? Let's just not even bother calculating lattice energy, but let's understand the relationship. Both of these have a chloride in it, right? So we have sodium chloride and we got potassium chloride. We have to figure out the charges and the size in order to know which one of these bonds is the strongest. So let's go do charges first. Well, if I look at the periodic table, I see sodium is a +1, and I see chlorine over here is going to take a -1 when it becomes a chloride ion, and I see that the K is a +1, and we know, because we just did it, that the Cl is a -1 too. So in terms of my value for Q1 times Q2, I'm going to get a +1 for both of these. Remember, we're taking the absolute value of the charges when we multiply them. So the big difference in what makes one of these bonds stronger than the other must be the size of the ions. Remember, your D is in the denominator. And remember, mathematically, if your D value is larger, your E value is smaller. So let's look at how your D value or size will affect lattice energy. So what's going to make a difference in the size of this ionic compound for each of these? Well, clearly, because your chlorine is in both of these, chlorine is not going to be what makes the difference in the lattice energy calculation. So we have to look at the size of each cation that's in here. So what do we know? So we know sodium is in the third period, which means it has 3 occupied principal energy levels. And we see here that potassium is in the fourth period, which means I have 4 occupied principal energy levels. That's going to matter because with 4 occupied principal energy levels, the potassium chloride is going to be larger than your sodium chloride will be, because potassium is larger than sodium. Now let's think mathematically. If this D value here is a larger number, this E value here actually winds up going down. So potassium chloride would have less lattice energy, while sodium chloride would have a smaller D value, which would make your E value bigger, and so that would wind up having more lattice energy. The greater the lattice energy, the stronger the ionic bond will be. Let me show you guys one more way that we can evaluate lattice energy. Let's look at which bond is stronger between sodium chloride and magnesium oxide. Let's go through our formula. Let's evaluate the charges. So for Q, I got a +1 and a -1, a +2 and a -2. So let's now play the game with this. We have +1 times -1. That gives me a -1 here, and that's going to give me an absolute Q value of +1. We have a +2 times a -2 here. That gives me a value of -4, which is absolute is +4. So they're telling you that the Q value here is much larger for the magnesium oxide that's there. You may be sitting there going, well, wait a second. The chloride ion and the oxide ion are in 2 different periods here. We have oxide in period 2 and chloride in period 3. Is that going to make a difference? Well, mathematically, it turns out that the Q values have greater impact on the lattice energy calculation than the size of the ions do. So when you are dealing with differences in the charge versus size, charge counts more than size does in terms of your calculation. So go with the charge. And we're able to see that here because if we look at the lattice energy calculation for magnesium oxide as compared to sodium chloride, it becomes super obvious that the magnesium oxide is indeed the stronger bond with a release of lattice energy of 3,890 versus sodium chloride, which is only 788. So if you're taking Regents chemistry, you can pretty much ignore everything I just taught you about lattice energy, because New York State is going to evaluate ionic bond strength in a slightly different manner, and they are going to do it based on what is called bond polarity, which is also known as your degree of ionic character. Bond polarity is calculated using something called END, which is an acronym that stands for electronegativity difference. So we are looking at the absolute difference, which means even if the difference is negative, we are going to make it positive between your bonded atoms in your ionic compound, and we're going to go look for those electronegativity values, as you guys know, on table S. And the relationship is pretty simple. The greater the electronegativity difference, the stronger the ionic bond will be. So if we are trying to figure out where we have a stronger bond, whether it is between sodium chloride or sodium bromide, let's go fish out some values. So sodium is the 11th atom here. It has a value of 0.9. So I know this one has sodium too. I can write that there. And I know chlorine, the 17th atom, has a value of 3.2. So I'm going to put a 3.2 there. And bromine is the 35th, and that's got a value of 3.0. So let's do our END for both of these. So 3.2 minus 0.9 gives me an END of 2.3. And in this case here, we have 3.0 minus 0.9. This gives me 2.1. So in theory, our sodium chloride is going to have the stronger bond because its electronegativity difference is greater. Now that we're armed with the understanding that an ionic compound has incredibly strong bonds, let's talk about all the rest of the properties, beginning with the fact that ionic solids have very high melting points. And that is due exactly to what we just learned before. Those ionic bonds that those ionic solids have are strong. And if you recall from the first slide, they're the strongest of all the primary bond types. And those Coulombic attractions between the oppositely charged ions in that lattice create incredibly strong attractions that will require a lot of energy to overcome. If you think about the lattice, each attraction between positive and negative ion will indeed have to get broken for one of these ionic solids to melt. Similarly, your ionic solids are also incredibly hard. They are hard crystalline solids at room temperature. Next time you're at a diner, pour some salt out onto the table, take the edge of the butter knife and try and break one of those crystals. It's pretty hard and you got to put a lot of pressure into it. And that's once again because the attraction between the ions in that crystal lattice is strong. Ionic compounds, even though they are strong, are also brittle, which means that your rigid crystalline structure will shatter when excessive force is applied. And to understand why, we have to look at the model of the crystalline lattice. So check this out. Here we have a hammer, and let's say we were to hammer this top row in the lattice and send it off towards the right. Well, if we were to hit it hard enough, that would actually shift these ions, and we would no longer have in this top row that juxtaposition of positive and negative ions. It's entirely possible, if we did push it, that we would have like-charged ions that were next to one another. Well, you guys know, if opposites attract, like charges definitely repel. And it is that repulsion between the like-charged ions when pressure will force them to be next to one another that will shatter that lattice and force the lattice apart. Another property of ionic compounds is that they are soluble in polar water. You should remember that water is polar from biology. And even though we haven't gotten deeply into it yet, we'll start to talk about what that means right about now. But what you have to know is that ionic solids will dissolve easily in water, and why has to do with your structure of your crystalline lattice and your polar water molecule. Check this out. You guys should know that water molecules, being polar, have charged regions about them. So the hydrogen side of the water is positive and the oxygen side here is negative. Well, when you drop a salt that is a crystal lattice into the water, you will notice the water leverages the charges that it has and starts to basically attract the ions that are in the lattice. You will notice that the positive hydrogen side of the water will attract the negative anion in the lattice, while the negative oxygen end of the water will attract the cation and pull it into solution. It's actually pretty cool if you think about it. Polar water molecules attract the oppositely charged ions of that lattice into the aqueous solution. And what we say is your ions that were once locked into place in that crystalline lattice now become hydrated, which means the water has picked them up, and mobile. They were immobile in the lattice, but mobile now that they have been hydrated means they are free to move, and that is going to be important in a second when we start to talk about conductivity. So for everybody playing along at home, the terminology when our ions in the lattice start to separate due to the water is dissociate. Kind of like you associate with friends. The water molecules are now causing the ions in the lattice to dissociate from one another, and that is creating our aqueous ionic solution. So now we would write something like this. We'd use sodium chloride, and now we would have to give it the aqueous designation because it is dissolved in water. This entire process is called an ion dipole attraction. The ions are the ions from the lattice, whereas the dipole is our polar water. Dipole because it has two poles. It's got the negative end of it and it's got the positive ends of it. Once your ionic solvent has been dissolved in an aqueous solution, it is now going to be able to conduct electricity. So let's talk about conductivity and ionic compounds. First thing you have to know is this: ionic compounds will not, I repeat, will not conduct electricity in the solid state. And that has everything to do with the fact that your crystal lattice has ions that are locked in place and cannot move. So if you were to introduce an electric field into the lattice, kind of like we're seeing here with this apparatus that's here, it's conductivity apparatus, that electric field cannot travel through the lattice. It can only travel through a medium that is moving. So in order to get it to move, well, what we have to do is either dissolve our salt or we have to melt it. So when you have an aqueous ionic solution or a molten ionic solution, now in the liquid state, your ionic compounds will conduct electricity. And it is all about the fact that they will contain mobile ions. Electricity now has the ability, with that mobile medium that it's in, to move freely through the solution. So please do not be that guy. Ionic solids do not conduct electricity, but they will when dissolved, and they will when they are melted. All right, that is it for properties of ionic compounds. Remember, if you found anything unclear, were wondering about anything, or you had any burning questions, make sure you bring them to the burning questions segment during our next session. It has been a pleasure taking you through properties. I will see you guys again on the flip side. Peace out.
That's all, folks.